So let's begin with the discussing the equation of motion first. So equation of motion, equation of motion can be given by mx double dot plus cx dot plus kx is equal to f naught sine omega t. So the solution of this equation is the solution of this equation the solution is x is equal to x dot e power minus zeta omega nt dot sine omega dt plus phi 1 plus a dot sine omega t minus phi. So this is the displacement equation. So this whole thing is the displacement equation. So when we are going to plot the complementary function with respect to the time, we are going to get the curve something like this. So let me do this thing first. So we will be getting curve when we plot complementary function with respect to the time, like this thing. So here you can see this is the envelope. And this is the varying amplitude. So this, we can say this is this is x naught, this is x1, this is x2, and so on. So basically this is the complementary function CF in y direction, and in x direction there is time. So this is called, so this nature of vibration is called transient, vibration. Now if we plot the particular integral with respect to time, then we are going to get plot something like this thing. So you can see that the amplitude here is constant, that is both have the same value here, both have same amplitude value. So we can we can say this is plus a, and this is minus a, and this is the particular integral in y direction. So this type of thing is, we can call it as steady state response. So this type of plot is called steady state response. Now if we combine these two graphs, if you are going to combine these two graphs, then we are going to get plot something like this, which I'm going to plot now. So the graph, after combining the complementary function and the particular integral, then we are going to get the graph something like this thing. So you can see this is a rough graph here. So this is a rough graph. So this is time, and this is x is equal to complementary function plus particular integral. So let's consider the system which we have taken earlier, uh, like this thing. This is m mass, and it is subjected to the force F naught sine omega t. So by the equation of motion, we know that mx double dot plus cx dot plus kx is equal to f naught sine omega t, and here x is equal to a dot sine omega t minus 5, which we have seen earlier. So this is the displacement of the system. So we can call this as a displacement of system. So this is the displacement of system, of this system basically. And the frequency of displacement of the given system is equal to the frequency of external excitation. So here A is equal to the amplitude of steady state response, or we can call it as a dynamic amplitude. Now moving forward, the things you should keep in mind, that the keep in mind stuff is that after sufficient time, the transient vibration will become negligible as it decays exponentially with respect to time. So the system So the system will oscillate. The system will oscillate only due to particular integral, that is pi. So this is the main takeaway for this thing. So we can so we can discuss more topic here, that is magnification factor. So let me start. So for the given system, we can write the dynamic amplitude, that is A, is equal to f naught by k divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So magnification factor, so we can define the magnification factor MF is equal to amplitude of steady state response divided by amplitude of steady state response divided by the static deflection. So in this case, static deflection is equal to f naught by k. So we can write the magnification factor. So let me erase this thing first. So we can write the magnification factor as magnification factor is equal to A by f naught by k. So after further simplification, we are going to get 1 by under root of 1 minus r square whole square plus 2 zeta r whole square. So let's discuss about some cases. So let's discuss about some cases here. So if magnification factor is greater than 1, then we can say that the dynamic amplitude is greater than the static deflection, that is f naught by k. And if magnification factor is less than 1, then we can say that the dynamic amplitude is less than the static deflection, that is f naught by k. So let's further discuss. So the magnification factor is the function of r and zeta. So if zeta is equal to constant, Then magnification factor is the function of R only. So for maximum or minimum, so let's calculate the case of for maximum, and or minimum magnification factor. So let's differentiate with respect to R is equal to 0. So d by dr is equal to 1 minus r square whole square plus 2 zeta r whole square power 1 minus 2. So let's further solve it. So let's further solve this equation. So minus 1 by 2, 1 minus r square whole square plus 2 zeta r whole square minus 3 by 2 in bracket 2 1 minus r square 0 minus 2r plus 2 into 2 into 2 zeta r dot 2 zeta equal to 0. So let's further simplify it. 2 1 minus r square minus 2r is equal to minus 2 into 2 zeta r dot 2 zeta. So 2 minus 2r square minus 2r is equal to minus 8 zeta square r. So let's further simplify. 1 minus r square is equal to 2 zeta square. So r square is equal to 1 minus 2 zeta square. So the r optimal is equal to under root of 1 minus 2 zeta square. So this is the equation of our interest. So so let's find out more. So let's find out more. So suppose let's draw a table. So this table is for zeta, and this is for our optimum value. So 2 4 5 1 2 3 4 5. Okay, so suppose if the value of zeta is equal to 0, then the value of r optimum will be 1. If the value of zeta is equal to 0.1, then the value of r optimum will be like 0.989. If the value of zeta is 0.2, then the value of r optimum will be 0.959 approximately. If the value is 0.3, then the value of r will be 0.9055. And if the value of zeta is 0.707, that is equal to 1 by under root 2, then the value of r optimum will be 0. So as you can see that as the value of zeta increases, the value of r optimal decreases. So this is the important fact. So let's talk about more. Okay, So here the magnification factor is equal to 1 by under root 1 minus r square whole square plus 2 zeta r whole square. So there are some special cases. So if r equal to 0, then we can say that r is equal to omega by omega n. So we can infer that if r equal to 0, then the value of omega is equal to 0. Then we can say that the value of magnification factor is equal to 1. Now second case is that if r equal to 1, that is, this is the case of a resonance, that is omega equal to omega n. So we can say that omega by omega n is equal to 1. So we can say that omega equal to omega n, which means which means the frequency of external excitation is equal to resonating frequency. So the frequency of oscillation is equal to natural undamped frequency of the system, which is the case of resonance. So this is the case of resonance. Now moving to the third case. Here zeta is equal to 0. That is the case of undamped system. So we can say the magnification factor in this case is equal to mod of 1 by 1 minus r square. Now the fourth case is if zeta is equal to 0 and r equal to 1, then we can say that the magnification factor in this case is infinity. The fifth and the last case is if zeta equal to 0 and r is equal to under root 2, then we can say that the magnification factor is equal to 1. So the few points you should note that the keep in mind stuff. Let me erase this thing first. So the keep in mind stuff, So the keep in mind stuff is that first point, for undamped system, the magnification factor will be maximum, that is infinite, at resonance. Second point is that for damped system, magnification factor will be maximum at like when r, that is the frequency ratio, is slightly less than 1, and the third case is that for damped system at resonance, magnification factor will be near to maximum. So this completes the this lecture. So in the second lecture, like in the next lecture, we'll be dealing with the force due to the unbalanced masses. So for now, thank you.